Hello and welcome to paragraph 2 about the history of the Earth. And in the first paragraph we had a look at the way our planet did form itself during the very beginning of our solar system. Today in the second chapter we will have a look at the history of our Earth through fossils. What are fossils and how are some fossils in good condition? What do we know and how do we know a lot about life in the unwritten past? What does the present tell us about the past? And then we are going to have a look at rock types, the rock cycle, and the difference between absolute and relative age. But we're going to start with the fossils. Fossils are very important for us because they tell us something about life that was here on our planet years ago. And as I've shown you in the first paragraph, there were types of animals which do not exist anymore today. Look at this picture where you see the skeleton of a trilobite or trilobite. These trilobites were pretty important during a long time in the history of our planet. And if we found skeletons or rests of these skeletons inside rock, it might tell us something about the condition they were living in. And by looking at rocks and fossils and try to understand why certain fossils are in certain type of rocks, we can explain things about how the landscape looked back then. To give an example, when you are looking at the south of the Netherlands, if you're going to Valkenburg, you might find the caves there, and these caves are actually embedded into big lumps of rock. And what kind of rock do we find here? This rock was formed during the Cretaceous period. That means that these rocks contain all kinds of fossils because the rock itself was formed by the parts that were left from the animals that were living there during that era. And of course you have to know that every human being and every being on our planet can be fossilized. But if this animal, or what kind of animal you're talking about, does have a skeleton, which of course contains chalk, or if it's got a shell, it will help us. Why is this? Well, these skeletons or shells could imprint themselves into the rock. So you can find a copy of the original animal embedded in the rock, or you are able to find the skeleton itself. And on the picture, the trilobite, that's its skeleton. But there are many more fossils to be found which are actually copies of the animal which was living there at a certain point in time. Well, the question is how to fossilize, because some skeletons were preserved in a very good condition. If you look at the fossil of this dinosaur, you might notice that you can see every bone it's got. But what is the reason for this? Well, the body of the animal has to be covered by sand or clay very quickly, so that there is less oxygen around him, and that means that the organic material does less disintegrate. It does not fall apart. As you might see, the flesh is gone, but if you have a closer look at the slab of limestone, you can even see that around his neck and near his shoulders are imprints of its flesh. So that means that you can see the way it looked with its flesh and skin on it, and you can see of course his bones, because these are not imprinted in the rock, but these are his real bones. But it has to be done very quickly. If there is more oxygen added to the skeleton, it will disintegrate more quickly and then it might disappear. So at that point of time you only will see an imprint in the rock. When you're looking at life in the past, rock formations and fossils tell us a lot about the climate in the past. For example, if you think of the image I showed you on the last slide, you saw that this dinosaur was embedded into limestone. Well, limestone can only form in a shallow sea with a high temperature and a lot of sea life, which of course we had in the Netherlands during the Cretaceous. But what if you're going to fish on the North Sea and you are finding the skeleton of a woolly mammoth? They couldn't swim. So that means that there wasn't a sea there at the point in time that these animals were living. So what does this tell you about the sea in the past? Many people tend to think that the woolly mammoth walked on top of the ice, but they did not. They were walking on the frozen solid ground, on the permafrost. And if you know that, you might think, okay, that means that the permafrost was there, and that means there was no water. And that's right. The water itself was embedded in a big slab of ice on top of Norway. And that means there was no water in the North Sea around our country. So these woolly mammoths could walk across the North Sea between the UK and the Netherlands. So if you're finding bones there, it means you might think, okay, these animals were crossing what we now call the border of our country. So it shows that the way a country looks can change over the years, because these woolly mammoths did not live that long ago. The woolly mammoth got extinct about 10,000 years ago, but not all got extinct. A small group did survive, and they were living on an island in the north of, near the North Pole, in the Arctic Ocean. And there they lived until 1700 years BC, so that is not that long ago. But then the climate changed again, and there wasn't enough food for these animals. And we all know what happens when there's not enough food. Animals die. But what does the present tell us about the past? As I told you, if you're going to Limburg, you will find limestone here, and limestone arises only when there's a shallow sea with a lot of sea life in it. So what does this tell you about Limburg? That this region should have had a sea back in the days. And that's not the only thing which is important. You may find some fossils here, like fossils from an ammonite, which is on this picture here. In this limestone, you might find an ammonite or its remains. So, if you had a look at the geological time scale, you might have noticed that limestone was formed during the Cretaceous, and that was 250 to 65 million years ago. And that means that this ammonite has lived during this period of time. And if you're not able to find ammonites in other layers of rock, this might tell us that these guide fossils only existed during this period, during the Cretaceous. So, if you hike to the top of the Mount Everest and you find a fossil of an ammonite, this means that this was a seabed and it was formed during the Cretaceous. So, if you're talking about guide fossils, they guide you to the information that you need to know in what era a certain species lived. And now we are talking about rock, and there are three main groups which are very important, because two of the three can't be used for finding fossils. and I'm going to explain to you why. But first of all, we have to look at them. We do have sedimentary rock, igneous rock, and metamorphic rock. These are the three main groups. Sedimentary rock is very important because this exists of layers of sand and clay, and they are compressed together. And after millions of years, the sand or clay will be transformed into sand or limestone. The same counts for the chalk, which is, of course, a result of sea life, what we were talking about earlier. And sedimentary rock is the only rock type in which you are able to find these fossils, because it's consisted of layers of rock, or layers of sand, layers of clay, which were compressed together. Now we're looking at the igneous rock, and igneous rock was once molten. If you take a look at the pictures, you might notice the difference. If there was a fossil inside the rock, that could not survive because of the fact that it is actually burned away by the high temperature of the molten rock. And you can divide the igneous rock into two separate forms. First, we do have the extrusive rock, which means that it was solidified on the surface. A form of this rock is pumice, as you see on the top right. And we do have intrusive rock, which is, for example, granite, which is on the right. And this solidifies inside the volcano or the crust of our planet. And of course, as I just said, it is impossible to find the remains of a fossil inside because of the fact that it was once molten. So that means that the limestone or the chalk in which the fossil was embedded is actually molten, and it changed its appearance into something which is unrecognizable. Here you see the metamorphic rock, and this contains both sedimentary and igneous rock, but it has changed due to very high pressure because of newly formed layers on top of it, and the very high temperature inside the crust. The rock can change. And what happens is that these layers are being compressed together, and what can happen is that it changes its appearance. And for example, limestone changes into marble. It's both the same base, it's both limestone, but it has another look because of the high temperature and the enormous pressure inside our planet. And now we're going to have a look at something else, which might sound a bit difficult, but it is not if you understand how it works. This is the rock cycle, and you may remember weathering and erosion from last year. And then there are two more things which might be new: compaction and sedimentation, and I will explain what happens. Please look at the picture on the right. You see at the top of this picture there's igneous rock, but this rock is on top of a mountain, and it is actually changed by weathering and lithification, which means that due to erosion and weathering, parts of this rock crumble downwards on the slopes of the mountain. They turn into sediment. But in time, these new layers of sediment could form a new kind of rock, which could be sedimentary rock, containing sand, containing clay, but not containing chalk, because we're not talking about limestone here. That only forms inside the sea. This sedimentary rock can change again because weathering and erosion affects sedimentary rock, of course, as well. So it can actually get back to sediment, or a part of it. On the other hand, at the bottom you see heat and pressure, which means that this sedimentary rock changes in its appearance into metamorphic rock in the crust of our planet. But this metamorphic rock can be suffering from weathering and erosion as well, so that means that again sediment can be formed. But if these rocks, these metamorphic rocks, start to melt, they can turn into magma. When that cools down, it forms new igneous rock, but that igneous rock can melt as well and creating magma as well. And the sedimentary rock and the sediment, it can melt all. That means that in this rock cycle, every step you see is capable of weathering and erosion, of sedimentation, of melting and cooling. And what does this compaction mean? Well, if you put layers on top of each other, they are compressed. This compression is called compaction because the layers tend to get thinner during this process. And now we're going to look at these rocks. These rocks are formed because of anything that could have happened during that rock cycle I've shown you. And as you might see, there are several layers visible here, and these layers tell us something about the history of these rocks. But do they tell us the age? Not yet. Because we can divide age in two different types. We can talk about the absolute and relative age. And when you are looking at the relative age of a rock, this means that you compare it to another layer. The upper layer is younger than the bottom layer, so it means that from bottom to top you got from old to new, most of the time. Sometimes that's not true, but most of the time it is. But when you're talking about the absolute age of a rock, this only can be defined as its real age, like I was born on the 25th of June 1987. So that means I'm 36 years old. Well, here you have to look at that rock and do several kinds of tests to say, how old are you? Well, I'm 65 million years old. As I just told you, most of the time the bottom layer of these layered type of rocks is the oldest, but that is not always true. When you are talking about compression, which of course happens in mountain ranges, it could happen that the bottom layer turns around, it flips and gets on top. At that moment you might have to think about the way this range has formed. But you can't say anything about how old is it. In that case you need the absolute age. And in that case you have to measure the radioactivity, the half-life of the rock. That helps a lot. But you can look at certain types of fossils as well. If you find a typical guide fossil inside a layer of sedimentary rock, it tells you enough, because we know at what point in time a certain kind of animal lived. But you cannot do that, of course, with the igneous or metamorphic rocks, because there are no fossils inside it. So in that case you have to look at the radioactivity or half-life. So this was it. I hope that you get an idea of how some processes in our planet work. It's quite difficult because there are so many processes, and all these processes lead to something else, that it's important that you have to divide it so that it makes it clear to you to understand. So what you can do is make groups for example, combine fossils and the type of rock that is important when you're talking about fossils. On the other hand, the rock cycle, what's happening there, and why is this rock cycle important to understand, why certain mountain ranges look different than others. All these kind of things can be made clearer if you make groups out of them. So that's something I think you have to do to get on with this. Well, as I just told you, this was the second paragraph, and of course we are going on with the second one later on, the third one, of course.